Every modern web page begins as raw data. Before colors are painted or layouts are calculated, an HTML document is an unstyled tree of data nodes. It's structural information meant for machines, completely devoid of visual design. To turn that raw data into a usable interface, web architecture relies on a strict separation of concerns. We keep the semantic meaning, the HTML, entirely separate from the mathematical rendering logic, which is handled by CSS. This diagram shows the rendering pipeline. The browser takes the unstyled document, applies layout rules, and injects typography and color to produce a styled interface. Looking at the code, variables like font family and color override default settings, calculating new values for text pixels. Bridging the gap between a raw data tree and a modern user interface requires mastering a few strict systems: mathematical color models, state-driven interactions, and structural box manipulation. Front-end engineering requires exact parameterization. When we assign a color to a UI element, we do not pick an arbitrary swatch from a digital palette. We calculate it. This breakdown shows how the base 16 hexadecimal system works. After the pound sign, 3 pairs of characters calculate the exact hardware-level light intensities for red, green, and blue. Double F represents maximum intensity, and 00 represents none. We can map these exact same hardware channels using RGB notation. Instead of base 16 pairs, RGB uses a standard numerical array from 0 to 255. The maximum intensity of red is simply 255, with 0 for green and 0 for blue. While hex and RGB speak directly to hardware, HSL maps color to human intuitive cylindrical coordinates. It positions the hue on a 360-degree wheel, then uses strict percentages to define how saturated and how light that color should be. This grid illustrates the programmatic advantage of HSL. By locking the hue at 195 degrees, developers can systematically generate exact UI variations, like hover states or borders, simply by shifting the lightness and saturation percentages. Understanding these overlapping vector spaces is how engineers write scalable color systems instead of guessing at hex codes. We apply that same systematic logic to text nodes. This tree diagram maps out how heading tags, H1 down through H6, establish a strict, machine-readable document outline used by parsers and accessibility tools. The visual sizing written in the CSS must align with this semantic structure. Skipping from an H2 directly down to an H5 just to make the text look smaller breaks the algorithmic outline of the page. Size is controlled by math. Tags are controlled by logic. This before and after comparison highlights the impact of spatial math on typography. By manipulating the line height variable to 1:6, we force a specific ratio of vertical space between text rows, immediately lowering the cognitive load required to read the block. Typographic styling engineers readability. It takes a raw string of text data and enforces a visual hierarchy that the human eye can instantly parse. Web elements are not static endpoints. They are state machines that must respond dynamically to user input over time. We control these interactions using pseudo-classes. These CSS selectors bind specific rendering parameters to discrete interaction events, like a cursor crossing the boundaries of a button or a user hitting the tab key. This flowchart details the strict chronological priority sequence required when architecting link states. CSS evaluates rules in order, so the unvisited baseline must be defined first, followed sequentially by visited, hover, focus, and active states. The hover pseudo-class provides immediate visual feedback. Exactly when the cursor intersects the element's bounding box, the CSS overrides the baseline color and text decoration to prove the element is interactive. But mouse interaction is only one input method. Keyboard accessibility relies on the focus state. Removing the visible outline from a focused element without replacing it breaks the interface entirely for users navigating without a mouse. Engineering these precise, overlapping interaction states provides a continuous, reliable feedback loop regarding what the system can and cannot do. We can also manipulate how entire components flow structurally. By default, browsers render HTML list items as stacked, bulleted, block-level elements. We override that default behavior with a single CSS declaration block. Setting list style to none completely strips away the semantic bullet markers. From there, applying a layout property like Display Flex will mathematically force the nodes to snap into a rigid horizontal configuration. A complex visual navigation bar is entirely an engineered facade. Underneath the spacing and interactive hover states, it remains a semantically pure HTML unordered list. This structural manipulation applies to dense data grids as well. HTML tables use specific tags, TR for rows, TH for headers, and TD for data, to define a strict relational matrix of cells. This mockup displays the visual noise created by default rendering algorithms. The double borders around every independent cell fragment the layout and obscure the data. Setting border collapse to collapse merges those independent borders into a single clean grid line, instantly improving readability. This CSS rule shows how we can programmatically inject zebra striping. The nth child even selector applies a specific background color to alternating rows, creating a horizontal tracking line that guides the human eye across dense matrices. Text and data aren't the only raw payloads. HTML also provides the audio and video tags, which act as native binary media shells embedded directly within the document object model. This code block demonstrates that these media tags absolutely require the Boolean controls attribute. Without it, the browser's native API is hidden, and the media interface remains entirely invisible and unplayable. Whether parsing a multi-axis data grid or exposing a native video player, CSS rendering rules and native attributes are what tame the raw payload for human consumption. A web page sent from a server arrives in the browser as pure, unstyled structure. It is chaotic by design, leaving all visual responsibility to the rendering logic. As the browser compiles the CSS object model, the first programmatic pass calculates and applies the color logic, painting the hexadecimal and HSL vector properties across the structural nodes. Next, typographic hierarchies lock into place. Text blocks scale algorithmically based on root font sizes, and line height variables inject calculated vertical breathing room between paragraphs. Finally, the structural pass takes over. Raw bulleted lists snap horizontally to form navigation bars, and noisy data tables collapse their borders to form refined, scannable matrices. Interface engineering is the programmatic application of mathematical state, structure, and color models. It is the mechanical bridge that transforms raw server data into the precise, interactive software components that make the web navigable.